Alright, morning everyone. Today we're going to be looking at rates of reaction and the different ways that we can measure the rate of reaction. This is guaranteed to come up in your exam as a question associated with the practicals, good ways to measure it, bad ways to measure it. You might be asked to write a specific method. So what we're going to do is we're going to run through all the different ways that we can do this in the lab to try and give you some pointers about how to answer those questions in your exam. So when we're talking about rate of reaction, we are generally talking about one of these 5 variables. We're looking at temperature, concentration, surface area, pressure, or catalyst. And we're going to try and look at each of those today, with the exception of pressure. We don't really look at pressure in the lab because we don't have the specialised equipment to be able to do things along those lines. The first reaction I'm going to do is I'm going to be adding calcium carbonate to hydrochloric acid. What are the products of this reaction? Now I'm asking you the question because I do want you to be thinking about the video as we go, so when I do ask a question you should think about it. If you really want to think about it and spend time over it, just pause the video, get a piece of paper, try and work it out, because this is all stuff that you should be able to do. So what are the products here? Our products are calcium chloride as well as carbon dioxide and water. Now you should also be able to construct a symbol equation for that. Now you might not know calcium carbonate, that's CaCO3. So if you want at this point you should pause your video, get a piece of paper and try and work out what the products are. We're not going to do that now though. Calcium carbonate with hydrochloric acid is going to be generating carbon dioxide here. And because it's generating a gas, that means the mass is going to change. How is the mass going to change? The mass is going to decrease. And the reason why it will decrease is because I've got a certain number of atoms, they're all there, they're being weighed. But as soon as the gas is being produced, those atoms are leaving the vessel, they're going off into the environment, they're not being weighed anymore. So, I've got a little weighing bottle here that I weighed out before. This is exactly 5 grams of calcium carbonate, exactly 5 grams. Now the chips here, they're a small size like that, small size. Then it's marble chips, so you might have seen this kind of thing on like a driveway, like in some nice driveways where they have small bits of stone, commonly in fish tanks. At the bottom you'll have chips that are just about that size. What I'm going to do is I'm going to pop that into my acid, and we're just going to keep an eye on the mass, and we're going to hit our stopwatch. So I've started again with 5 grams exactly, and already I'm down to about 4.98, and as the reaction gets going, that will change as time goes on. Now what I'm going to be doing is, I've got 2 ways of measuring this rate. Either I can take the rate every, say, 30 seconds. So as soon as this hits 30, I'll look at the mass and I'll write that down. When it hits a minute, I'll look at the mass, I'll write it down again. Alternatively, what I can do is I can just wait till a certain amount of time has gone. So I say, well, I'll just do it for a minute and I'll see how much the mass changes, or I'll just do it for 5 minutes and I'll see how much the mass changes. Either is absolutely fine. Okay, so let's say I wanted to wait for 1 minute. I'm now at 45 seconds. I've got another 15 seconds to wait, and then I would hit my stopwatch. And again, I'm not going to hit it exactly 1 minute because it doesn't really matter, and I'll take my mass, which is 4.95 grams. So I've started with 5.00 grams, I've now got 4.95 grams, I can then calculate my rate of reaction. My next step would be to change one of these variables. So I've done it for chips that are this size, I've done it for a specific concentration of acid, and I've done it at room temperature. So if I wanted, I could do the whole thing again, but before I put the chips in the acid, I could warm it up. And I could do my reaction at, say, 20 degrees, at 30 degrees, at 40 degrees, and at 50 degrees. Alternatively, I could change the concentration of the acid. I could say, right, well, I've started with acid which is a concentration of 0.5 moles per decimeter cubed. Don't worry too much about that unit, you're going to learn more about it later. But I started with acid that's concentration 0.5, now I'm going to do it with 1.0. And then I'm going to do it with 1.5, and then I'm going to do it with 2.0, or whatever concentrations I chose. Surface area. So I've done it with chips that are at quite a small size like that. But if I wanted, instead of doing small chips, I could do it with much bigger chips, or I could do it with my calcium carbonate here, which has actually just been ground up as a powder. Which one of these, small chips, large chips and powder, is going to have the biggest surface area? The powder is going to have the biggest surface area. What that means is that will have the greatest rate of reaction. The large chips will have the smallest surface area, there'll be the smallest amount of calcium carbonate that's available to collide with the acid. It will have the slowest rate, or it has the smallest rate of reaction. Again, pressure, can't really do that in the lab, so we'll leave that for the minute. And then finally I could use a catalyst as well, which we will get to a bit later on. Okay, our next experimental apparatus that we're going to be using is a technique called collection underwater. Now, I could measure the mass, which is what I just showed you, but also I can measure the volume of gas that's being produced and how long it takes for that gas to be produced. There are two ways to do that. I'm going to show you the first one and then I'll do the second one. The first one is called collection underwater. Essentially what I do is I have a measuring cylinder that's full right to the top with water. Now I need to get this to be the other way up and underwater, so I'm just going to put my hand on it like that, and then I'm going to stand it up in the water bath over there, and I'll put the grades over there so that you can see those measurements. And so, do you mind just getting me a piece of paper towel so I can dry my hand? Yeah. Thank you. Now I've got my acid just like last time, and I've got my calcium carbonate just like last time, and I'm going to be popping my calcium carbonate into the acid. Now as soon as that reaction starts, the gas is going to be produced. Now before, when we did it before, the gas just went off into the atmosphere. But what I can do is I can collect that gas into my measuring cylinder, and I do that by using a delivery tube that looks a bit like this. What I'm going to do is I'm going to add the marble into the acid. I'm going to hit my stopwatch. I'm going to hit my stopwatch, and then once the reaction starts, the gas is going to be produced. It's going to come up through, I'm going to put the bung in here. The gas is going to come up through the tube and into this measuring cylinder. So I'm going to set that up in here first. So I'm going to make sure my tube is really nice into the measuring cylinder. If the tube is not in the measuring cylinder, you don't get the gas that you wanted. It just goes off into the atmosphere, bubbles through the water instead of going off into here. Similarly, another problem that you often see with this is if there's a gap here. It needs to be completely full with water, there needs to be basically no air there at all, otherwise you get an inaccurate measurement. So, I'll be doing this with a partner, and I would ask them to hit the stopwatch as soon as I started the reaction, and I'm going to ask Mr. Orr to hit that for me. Okay, and I'm going to pop that in, put my bung on. Now the reaction is going to get started. Thank you, sir. And I can see that it's fizzing, I can see that it's bubbling. Can I have another of those blue towels, please? I can see that it's fizzing, I can see that it's bubbling, so I know my reaction started. I haven't got any gas yet coming through, so I need to wait. It's going to expand, it's going to fill the bottle. Now remember, I'm doing this with these small size chips. I could do it with any size chip, and I can see already now that gas is starting to be formed. So you can see the bubbles coming up. Now what I might do, again like before, is I might say, right, well, every 30 seconds I'm going to see how much gas has been produced, and I just go to the measuring cylinder and I see, oh right, well, that is now at 8 or whatever. It's unfortunately the gradings don't go down to 10, so I'd need to wait obviously until it hit that point. Or I could say, right, I'm going to leave it for 5 minutes and see how much gas has been produced. Any way is fine, so long as you're fixing your time and you're getting a measurement for the volume. What I'd do next, again, is I'd fix up one of these variables. So I might change the temperature or the concentration or whatever. I also need to think about the things I'm going to keep the same. So let's say I wanted to change the surface area of the marble chips. So I wanted to go from small ones to big ones. The things that I need to keep the same are the mass of marble chip that I'm using, the volume of acid that I'm using, and I want to use a measuring cylinder to make sure I get the same volume every time. Which particular acid I am using. Am I using hydrochloric acid, nitric acid, phosphoric acid, sulfuric acid, whatever acid I'm using, I'm going to want to keep it the same. And then all these other variables. So if I'm changing the surface area, I want to keep the temperature the same, the concentration the same, the pressure the same, and I want to use no catalyst. Another interesting one is stirring it. If I stir it, I'll increase the rate of reaction. If you've got your lump of calcium carbonate and there's acid all around it, it's only reacting with the acid that's around it right there. When I stir it, I allow it to be able to react with more of that acid. So if I stir that, I'll get more vigorous bubbling. So if I want to stir it, I need to make sure I'm stirring it in every single reaction and with about the same amount of strength. Obviously that's very difficult to control. So that's definitely something that you'll need to be thinking about when it comes to it. So my reaction's done, and I'll just take off the bung, and let's say it was 2 minutes, so I'd stop it at 2 minutes, and I'd record my volume here, which is a bit difficult to read now, but it's there at 79 centimetre cubed. So I've got 79 centimetre cubed, it took me 2 minutes, I do one divided by the other, and I get my rate of reaction. Okay, my next one is very, very similar to the last one. It's just a different way of collecting the volume. Okay, so the previous way was collecting it underwater. Now that's a great technique, but the problem with it, you can get water everywhere. It can be a bit difficult to set up. There's error in terms of if you let a little bit of gas get into that measuring cylinder to start with. So sometimes what we like to do is we like to use a gas syringe, which can be a little bit easier to read and definitely a little bit easier to set up. So I've got again my acid, and I've got again my marble chips. So I'm going to do exactly the same thing. I'm going to add one to the other, put the bung on. As soon as the bung goes on, the gas is going to be produced, it's going to go through the tube, it's going to go into the measuring cylinder, it's going to push it out like this. Now, because that measuring cylinder only goes so far, what I might want to do is I'll say, right, well, I'm just going to time it, how long it takes before it hits a certain point. So I might say, well, as soon as it gets to 50, I'm going to stop my timer. So what I'll do is, I'll get everything ready, I'll pop my marble in, I'll hit my timer, and again, as before, the reaction is taking place. Calcium carbonate, hydrochloric acid, calcium chloride, carbon dioxide and water. Gas is being produced, and I can see already that my gas syringe is starting to be pushed out. So you might not be able to see it so well on the video, but it's definitely coming out over here, nice and slow. Now what I'll do is I'm going to wait till it hits 50 and I'm going to hit my stopwatch. I'm then going again to change a variable, so I might change the temperature of the acid, the concentration of the acid, the surface area of the marble chips, whilst keeping everything else the same. And that way I get a nice range of results for the different variables. So I've given that now, I'll get 40, it doesn't matter, I can say, right, I'm going to pause it a minute and see how much I've got, or I can wait till it hits 50 and stop it there. Now in this case, for the sake of time, I'm going to wait till it hits 40, and boom, done. 51 seconds, 44, and I'd record that in the table. Now the reason why the gas syringe is useful for this is because there's not bubbles, it's going up really gradually. So I know when I pause it that I'm getting a really precise reading, and I know that I'm not reading it and there are more bubbles still to come. So it just can give me a better reading. Doesn't always, but it can give me a better reading if your experimental technique is good. The final one we're going to look at in terms of the normal reactions that are asked about in an exam. So very often you'll see mass on a balance, you'll see collection of gas underwater, collection of the gas syringe, or you'll see this, which is called the disappearing cross method. And these are the ones that often come up. Disappearing cross method is very straightforward. You're doing a chemical reaction that results in the production of a solid. Why is that important? I've got here a solution of sodium thiosulfate. Now because it's a solution, it's clear. It means you can see through it, no problem. So if I put a symbol behind it, you'd be able to see that, no problem. I've got in the flask, I've got an acid, which again is a solution, it's clear, you can see through it, no problem. So when I put that cross behind it, you can see through it, no issues. But when these two react together, they form sulfur, which is a solid. And they form as very fine particles, so like a powder. And that kind of spreads out throughout the solution. And because that's a powder, that's a solid, you actually can't see through it. And that means that eventually that cross will disappear, and I won't actually be able to see it anymore. I've got two different concentrations of sodium thiosulfate, which is what I'm going to be reacting with my acid. Acid in here, sodium thiosulfate there. This one is very concentrated, and this one is much less concentrated. This one's about 10 times as concentrated as that one. What I'm going to do is I'm going to pour them both in at the same time. I'm going to hit my stopwatch, and I'm going to see which one clouds over first. And then I'm going to hit the stopwatch for that, I'll lap it, and then I'll do the stopwatch for the other one as well, and I'll get two different times. Okay? So, sir, do you want to zoom in so that you can see all those?
Hold on, I'm twisting it the wrong way.
Okay. Now if you tighten it up again, the camera will roll over. Good. Alright, so I'm getting ready to add these in, and I'm going to hit my stopwatch and pour them in. Remember, this one was really concentrated and I can't see the cross anymore. So I'm going to lap that at 11 seconds. I'm going to keep this one going. So I would write down for that one it was 11 seconds. Now, if you were to do this practical, you would not do them both at the same time. There'd be two of you, you'd be doing one, then the next one, then the next one, then the next one. What you'd want is to make sure that you're keeping a really careful eye on that cross, making sure you're trying to get really precise and consistent with the exact time that you can't see it anymore. And then because you're doing it one at a time, it means you're getting a much better time for each one. Now, you can see how quickly that one went, and this one is still going and still going. If I leave it for longer, then eventually this will go cloudy, and I can see it's getting a little bit cloudy, but not a lot. We give it a really nice stir, but it's still going to take a while. So it's starting to get cloudy, but it's going to take forever. So what we'll do is we'll speed up the video in post-process. I can't see the cross anymore, so I'd stop my timer. And you can see that one took 2 minutes and 17. So the one that was really concentrated, very quick, 10 seconds, 11 seconds, whatever it was. This one, very slow, over 2 minutes. So what I'd want to have done is I'd want to have done it with a whole range of concentrations of sodium thiosulfate. I'd want to have kept the concentration of the acid the same. I'd want to have kept the temperature the same, the volume of each that I was adding. I would have kept everything else the same, just changing that concentration. The one from last practical that I want to show you, and this isn't one that comes up in your exams, okay, but I just want to use it to demonstrate exactly what's going on here. I've got some glow sticks, okay. Now what a glow stick is it's 2 tubes of plastic. You've got a big tube of plastic, and then inside it you've got another tube of plastic. In the big tube of plastic you've got chemical 1, and in the little tube of plastic you've got chemical 2. When you crack it, what you're doing is you're breaking the inside tube and you're allowing the chemicals to mix. And when chemical 1 reacts with chemical 2, it produces a chemical reaction which releases light because it's exothermic. It's moving energy to the surroundings. I've got 3 different glow sticks here which have all been sitting there getting used to the temperature that they're in. I've got one that's set in an ice bath, one that's at room temperature, and one here that's in boiling water. What I'm going to do is I'm going to crack them all, shake them up, and pop them back in. What you should see is that the rate of reaction is much quicker in the one that's really hot. Now, if every time a reaction happens it releases a little bit of light, if there are lots of reactions taking place, we're going to release a lot of light. So you should see that this one's the brightest. Now over here, what you'll see is that the reaction is really slow. The reaction is still taking place, but it's really slow. Because it's so slow, only a little bit of light is being released. Because the collisions are infrequent. Every time they collide, they're releasing a bit of light, a bit of light, a bit of light. But because there are so few of these collisions, we're not going to get a lot of light overall. And hopefully, that's what we'll see. So what I'm going to do is I'm just going to crack this one up. Give it a really nice shake. And pop it in. I'm going to do the same for this one. I'm going to turn the lights off in a second so we can see. Give it a really good shake. And pop it in. I'm going to do the same for this one. I'm going to crack it up. Give it a really good shake. And pop it in. Now what you should be able to see on the screen is that this one here is clearly a lot brighter. Between these two, you can't really see that much difference, but from where I'm standing it does look like this one, the middle one, is a bit brighter than that one. But it's really clear that the one that's really hot has the greatest amount of light coming off it. And actually when we separate them out a bit, it might be even easier to see that there's a kind of a big glow around this one. The glow around this one is about this big, but there's basically no glow around this one at all. So it is the case that the hottest one, the reaction is taking place quickest. Now again, the reaction is still taking place in the middle one and the cold one, but because those collisions are really infrequent, only a little bit of light is being released. Pause the video. Alright, the final reaction we're going to look at involves the use of a catalyst. We are starting with a compound called hydrogen peroxide, which is H2O2. Now, over time, hydrogen peroxide is not stable, so it actually breaks down and it forms water and oxygen. H2O plus O2. Now to balance that, I'm going to pop a 2 over there and a 2 over there. That happens naturally over time. So if I have some hydrogen peroxide in a flask like this, over time that's going to generate oxygen. Now normally when the oxygen is generated, it just goes off into the atmosphere. So this is, at the moment, generating oxygen. Not a lot. Now if I pop that into a cylinder like this, again it's still generating oxygen, just not a lot. What I can do is I can try and capture that oxygen by using washing up liquid. And what the washing up liquid does, it just kind of allows the oxygen, instead of escaping out, it allows the oxygen to make a kind of foam. Now what you can see is that nothing is happening there. What I'll do is, I've got another portion of hydrogen peroxide, and I'm going to add it to my measuring cylinder here. And I'm, again, going to add some of my washing up liquid. And make a foam. Now again, if I came back in 2 weeks' time, both of those would have produced the exact same amount of oxygen, because I use the same amount of hydrogen peroxide. It would take a week. It's really slow, but it would happen over time. So how can I speed this up? Well, one thing I could do would be maybe to increase the temperature. But I can only increase the temperature so far, because once it hits 100 degrees, then things here start to boil, and that's no good. I could change the concentration, but actually, I've got the most concentrated hydrogen peroxide I can find, so that doesn't necessarily help me. Surface area, I don't have any solids, so I can't do that. Pressure, again, I can't change that in the lab, which leaves the last thing as catalyst. Remember, what is a catalyst? A catalyst is a substance which speeds up a reaction, it increases the rate of reaction, but is not used up itself. For this reaction, I can use a catalyst called potassium iodide. And with any luck, when I pop that in there, now that going on there is this reaction. It's just quicker. Because I've added my catalyst, the reaction is incredibly fast. The oxygen is being produced, it's being held by that soap and making a foam instead of just going off into the atmosphere, but it's still there. That reaction is exactly the same as what's going on there. If I managed to find a way to extract all the potassium iodide, I'd have exactly the same mass as I started with. It's just a catalyst. But you can see just how much quicker the catalyst makes that reaction go. If I left this one for a week, I'd generate the exact same amount of oxygen. But this one goes in seconds and it's finished. This one takes a very long time indeed.